Okay, problem 1 on the practice exam looks like this. There's 2 versions of problem 1, or 2 different kinds of problem 1, so I'll go over both of them in this video, and then in subsequent videos I will go over similar concepts for problem 2, 3, 4, etc. So, problem 1, what is the Euclidean space of these set of vectors? The Euclidean space is how many numbers they have. So A is R4. The scripty R means a set of all real numbers, and there's 4 numbers in each vector, so it's R4. What are the coordinate unit vectors of that space? So these are the ones that define the coordinate system, and they look like this, where each unit vector has 1 non-zero entry, and they go through one at a time. So the first location, and the second location, the third location, and the fourth location. Determine the unit vector of V1. So V1 looks like this. Unit vector, or V looks like this. A unit vector, the unit vector V is 1 over the norm of V times V. So I need to find the norm of V equals the square root of all the elements squared. So 16 plus 0 plus 9 plus 0, that would be the square root of 25 equals 5. Which means UV is going to be all of my elements divided by 5. So negative 4 over 5, 0 over 5, 3 over 5, and 0 over 5. I can write this in decimal point, 0.8, 0, 0.6, 0, etc. There we go, there's UV. D. Determine whether V1 and V3 are orthogonal or not. Orthogonal means they're perpendicular. If we think about the equation for the angle, cosine of theta equals u dot b over the norm of u times the norm of v. If they're orthogonal, that means this is 0, so u dot v should equal 0. So if I take the elements of u, multiply them by the elements of v, and add them all together, I have negative 4 times, v1 and v3, so this one and this one. Negative 4 times 0 plus 0 times 0 plus 3 times 0 plus 0 times 9. That equals 0. Therefore, they are orthogonal. E. What is the distance between u, or v1 and v2? So the distance equation looks like this. Doesn't matter which one comes first, because it's going to be normed anyway. So v1 and v3. So now I'm looking at these 2 vectors. So negative 4 minus 0, 0 minus 6, 3 minus 0, and 0 minus negative 8. Negative 4, negative 6, 3, and 8. If I take the norm of that, it's the square root of all the elements squared, so 16 plus 36 plus 9 plus 64. You can bring a calculator with you to the exam as long as it's a non-graphing calculator. I can do this in my head or on the side, but for brevity's sake, I'm going to type it in so you guys don't have to sit me watching. So 125, I believe that's a perfect square. Maybe it's not. Nope. So it's not a perfect square. I can leave it like that, totally fine. It's also 11.18. Either one. I don't care. So you can leave it like this, which I would encourage you to. It's an exact answer. Or you can leave it in the decimal form. Either one. Same thing up here. You can leave it in the fractions or you can leave it in decimals. Does not matter. E. F. Okay. Using the determinant, determine whether your vectors are dependent or independent. So if we want to find the determinant, we just take all of our vectors and plug them into a matrix. So I know V1 looks like this, 4, 0, 3, 0, because I have it written here. V2, zoom out, 0, 6, 0, negative 8. You obviously won't have this problem on your sheet of paper. There we go, there's my matrix. If I want to find the determinant, then what I'm going to do is I'm going to pick a row or a column with the most number of zeros. So I'll pick this column here. which means my determinant of this matrix is going to be 9. Let's see, times its cofactor. So C, it's in row 1, 2, 3, 4, in column 3, so 4, 3, plus 0, plus 0, plus 0, because all these elements are 0. So C4, 3. Remove the row, remove the column. My remaining elements are going to be negative 4, 0, 3, 0, 6, 0, 4, 6, negative 3. And then if I determine my sign, it's going to be plus, minus, plus, minus. So that's a minus, plus, minus. So it's a negative, changing my sign. So I'm going to go ahead and use my shortcut method. Does not matter which method you use to find the determinant of a 3 by 3. It is a 3 by 3, so I can use my shortcut method. So these elements, 4 times 6 times 3, 72, plus these elements, 0, plus these elements, 0. Minus, I'm not going to forget my minus out here. These elements, these elements, and these elements. So 0 plus 0 plus 4 times 6 times 3, which is 72. So I have 72 minus 72 equals 0. Negate that, negative 0. Okay, so my determinant here is 0. Therefore, S is dependent. Which means these vectors are linearly dependent, which means I can write them as a linear combination. And we can see, I don't know, I think it might be V1 plus V2 plus V3 to get V4, something along those lines. Not quite the case. Actually, yeah, I think it might be. V1 plus V2 minus V3 equals V4, or maybe it's minus V2. Anyway, I can write them as a linear combination, so which means the answer to G here, G, based on your answer to part F, can the vectors be written as a linear combination? Yes. Because they are linearly dependent, and the determinant of A equals 0. Okay, that is question number 1. Question number 1, solving through all of it. Part B, consider 4 vectors in R5. These vectors are placed in the rows of a matrix. So 1, 2, 3, 4. So it's 4 rows, and each row has 5 elements. So this matrix is 4 by 5. If the rank of A is 3, answer the following questions. So my rank is 3. Is the set of vectors linearly dependent or independent? They are dependent because rank of A equals 3, which is less than the number of rows, the number of vectors. B, true or false? None of the 4 vectors can be written as a linear combination of the others. False. Same reason as it was above, because they are linearly dependent. So just like above, we can see that they're linearly dependent, which means they are linear combinations of each other's, where I can say C1 V1 plus C2 V2 plus C3 V3 equals V4. These constants here, C1, C2, and C3, these are not all 0. They're not all 0, so it doesn't matter if it's just one of them that's not 0. Somehow I can use V1, V2, and V3, add them all together by multiplying by constants to get to V4. Okay, there's the 2 versions of problem 1. You can see starting to explore the general vector math that we talked about in week A, and also going through linear combination stuff, talking about dependence and independence stuff that we went after in week E.